I think this one is okay.
Okay.
Whichever one you want.
No, that.
Interesting.
Good morning. Good morning, everyone. Welcome to this distinguished talk presented to you from the NUS IDM Network and Faculty of Engineering. We have a very distinguished seminar by Dr. Alan Kay on grand challenges in future interactive digital media, creating the next 500-year revolution after printing. Well, you probably already know Dr. Alan Kay so well because he's one of the most famous people in computer science, but let me just say a few words. He's one of the earliest pioneers of object-oriented programming, personal computing, and graphical user interfaces. His contributions have been recognised with the Charles Stark Draper Award of the National Academy of Engineering for the vision, conception, and development of the first practical network personal computers. He also received the prestigious Alan M. Turing Award from the Association of Computer Machinery for pioneering many of the ideas at the root of contemporary object-oriented programming languages, leading the team that developed Smalltalk, and for fundamental contributions to personal computing. And he also received the prestigious Kyoto Prize in Japan from the Inamori Foundation for creation of the concept of modern personal computing and contribution to its realization. He's been a Xerox Fellow, a Chief Scientist of Atari, an Apple Fellow, Disney Fellow, and HP Senior Fellow. In 2001, he founded Viewpoints Research Institute, a non-profit organisation dedicated to children and learning. And he's currently an adjunct professor of computer science at UCLA and a visiting professor at Kyoto University and an adjunct professor at MIT. He's been elected a Fellow of the American Academy of Arts and Sciences, the National Academy of Engineering, the Royal Society of Arts and Computer History Museum. And he's received many other honours, such as the ASM Systems Software Award, NEC Computers and Communication Foundation Prize, Funai Foundation Prize, and many, many others. The list is endless, actually. So I'm sure you agree, it's a very prestigious and distinguished speaker. We look forward to his talk. Please make him very welcome, Dr. Alan Kay.
Thank you. It's amazing to still be alive. Actually, one of the great inspirations for all of us, I think, is Doug Engelbart, the guy who invented the mouse, but the mouse was the least of his great ideas. He just had his 82nd birthday yesterday. So he's still hanging in there, and I sent him an email saying, just stay alive, Doug, eventually they'll understand your second idea. That's a way of saying that people have a real difficulty in dealing with the immensity of what already is, and especially if what already is a lot of it is somewhat random, it's still there. So it's interesting that a person can spend their entire life doing nothing but learning what's inside of Linux. And it could seem like the entire intellectual horizon in computing because it's just endless and wall to wall, but in fact hardly has any ideas in it at all. So one of the tricks is to try and figure out how not to get overwhelmed by the stuff that's around. And we also are in a very pragmatic environment, pretty much always have been in computing. Maybe more pragmatic today because there's so much money to be made from it. And so there is a real tug and pull for people to be incremental on what already exists. Most jobs are to be incremental on what already exists. And it's hard to explain to people that, for instance, in the early 60s, there were no personal computers, there was no internet, but there were plenty of computers around. There were different kinds of computers, and what people thought computers were about were different. So somebody back then had to decide that what IBM was doing and what Burroughs was doing and UNIVAC was doing wasn't the entire story about computing. Somebody had to do something that wasn't incremental, and somebody had to fund those people who we're going to do this stuff that wasn't incremental. So this talk is both about things that we could think ahead about, but it's also about how we get the resources and convince the people of what they need to know in order to sorry, let me just okay. So I'm part of a research institute we set up 6 years ago now, called Viewpoints Research Institute, and it was set up to imitate the research processes that were so effective many years ago and which no longer exist, at least in the United States, in any organized fashion. So in the 60s, this was the kind of stuff that was in the air. And if you look at the topics in brown, the brown lettered topics, they all look pretty reasonable. Advanced programming, yeah, we should have better operating systems. We should have more pervasive networking, user interfaces. All these things are good topics, and kind of the theory about how they were going to be done and what it meant to meet some of these challenges, I put in blue here. And it's kind of interesting. If you look, for instance, at networking, the networks that existed back then were telephone networks, and they were switched. And the world's largest computer company did everything half duplex. Half duplex means that if you type a character, it goes wherever it's supposed to go, and you don't get any acknowledgement back that that character made it. So if you're... This came out of basically the very first teletypes, which were stupid enough so that when you hit the key, they just printed the character that you hit and also send it. And they pretty soon discovered that that didn't work all the time, because the character sometimes didn't get to the other end, but it would show up on your little piece of paper. But on the other hand, if you made a perfect transmission line, then you could get away with this. And star networks from big mainframes were popular, and IBM was starting to work on a ring network. Better operating systems for time sharing, hardware, bigger mainframes. So Moore's law meant to most computer companies that they were going to make a bigger profit on their mainframes because the components would be cheaper. They could sell these big, huge, faster processors. Let's share these things because of economies of scale, and so forth. The programming area was all about making better ways of describing data, because that's what people had been doing. Abstract data types, relational data. Let's make programming more structured, and so forth. So the interesting, and the majority of the research money in the 60s went towards this stuff. For instance, there was an enormous amount of effort. I should have put parsing in there, because that was really big back then, and a lot of university professors made their reputation by coming up with a new and different way to parse that you could write mathematical things about, and so forth. So an exception to this was basically ARPA, Information Processing Techniques Office, and the Office of Naval Research. So one of the things they funded was the development of one of the very first interactive graphics systems called Sketchpad. The machine that Sketchpad was done on, that this guy, Ivan Sutherland, is sitting in front of here, is about twice the size of this room, and volumetrically. So it was about half the size of a football field. And they thought a lot of Ivan, so they let him have this entire machine from 3 o'clock in the morning to 6 o'clock in the morning. And we call that when there was only one personal computer. And if I had 2 hours to give this talk, I would show you some demos from back then because they're still quite shockingly good. And the other thing that was in the air in the middle 60s was that Licklider there, the first guy, the guy on the left, who was doing the main funding, and Bob Taylor, who was his deputy, had decided they needed to invent an intergalactic network, as they called it. So their idea was, let's not fool around being incremental. Networking is at its most interesting if you can, today we would say put an IP address on every blood cell. Right? If it's there, you should be able to communicate with it. So Licklider always called it the intergalactic network so that the research scientists wouldn't think too small. And there was no way of doing a switch network like the telephone system that was going to work for it. So that was very helpful. This thing was too difficult for current techniques. And that turned it immediately from a development, a D, into an R. You don't want to confuse R and D. Today they mean the same thing. Most companies call, when they say R&D, they mean product. They're precious little development and zero research. But the way to force yourself into doing research is to pick something that is impossible but desirable. And these two crazy guys, Dahl and Nygaard, back in the early 60s wanted to simulate entire oil refineries on computers, which was regarded as completely nutso. So oil refineries have thousands and thousands and even millions of parts. And a lot of them are active simultaneously. So they came up with a programming language called Simula that was a modification to ALGOL, but it was also a point of view shift, a way of thinking about what it might be to do computation in a very different way than functions and data structures. And when I came on the scene in the mid-60s, my background was in mathematics, pure math actually. I had a degree in pure math, and I had another degree in molecular biology. And so the two things I got from that is the pure mathematician hates anything that's larger than this. So the idea is find the abstractions that will take this and make it into this so you can think about it. And the biologist hates mere mechanism because the cells in the body, both internally and externally, make something more interesting than a Swiss watch. So virtually every mechanical metaphor we have for mechanism has involved something like gears and tight couplings and tolerances and all that stuff. And biology says, forget about that stuff. We want to build 100 trillion cell organisms, and we don't care if the individual cells have 60 billion parts. So once you understand what those numbers actually mean, they completely liberate you from any computer thoughts. It's just the scale is just completely outside of computer thinking. And then what that means is you can actually start thinking again. Most people, when they think, they look up a memory, or they look up somebody else's opinion. So the hard thing is to actually do real thinking. And the hardest part of doing real thinking is to set up mechanisms that will tell you when you're not thinking. Most of the time when we're thinking, we think we're thinking and we aren't thinking. It can get confusing. So when I saw these things, I had this kind of mystical realization that, wow, if you just didn't worry about how hard it is to compute, then abstractly every doggone thing here, 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 inside the computer, outside the computer, is actually kind of like computers sending messages to each other. And so the thing I got onto was the idea is, boy, if you could make little software computers that were efficient enough to be runnable, you would actually have a scalable architecture where you could do the smallest things that you needed to do on your computer, and you could model the entire galactic network that was going to happen. And a short time after that, Ed Cheadle and I started working on this desktop machine. This is a picture of it on its own display. So you can see one of the interesting things about displays back then is that they weren't raster displays. And the reason they weren't raster displays is that 300,000 pixels was an unthinkable number of pixels. You couldn't write them fast enough, and the memory in the 60s was more than $1 a bit, etc., etc. So these are line drawing displays, and this is what this machine looked like. But I used this object idea to make an object-oriented operating system for it, and it was late-bound, and it had Windows, and had a tablet, and influenced by a lot of other ideas. So it was an early personal computer. And one of the things that Cheadle and I thought would be great is if we could make this thing usable by non-professionals, as well as professional engineers. And so I ran into various people who were dealing with non-professionals, but the most interesting one was Seymour Papert, who was dealing with children. And Papert was a mathematician, and he'd come up with a number of ideas, but he basically was trying to teach children how to do advanced thinking of a mathematical kind by actually making things out of computer stuff. And he had both a physical turtle and a display turtle. And so one of the things he would do with a child, a 6-year-old child, he'd say, okay, close your eyes and make a circle with your body. So the kid would start doing this, and Seymour would say, okay, what are you doing? And the kid would say, well, I'm going a little, turning a little over and over again. And in Logo, going a little is forward 5, and turn a little is turn 5, over and over again is repeat. So if you execute this Logo program, now, of course, the kids think it's going to spiral, especially if they change the numbers. We'll get to that in a minute. So I'm sitting there thinking, holy shit. Seymour is teaching 6-year-old children differential geometry. In fact, the differential geometry of vectors. Why did he do that? Because he studied with Piaget for 5 years after he got his PhD in mathematics. And he learned something about the way children think about the world. And if you ever had fun playing with a child, you realize they're delightfully narcissistic. The narcissism is less delightful when they become teenagers and odious when they become adults. But in a 6-year-old child, there's nothing more fun than a self-centered little child. And self-centered people think they're at the center of the universe. And Papert said, aha, Carl Gauss went from an external geometry with reference to an external coordinate system, like a Cartesian one, to an internal one, which was a reference to some point or state. And so when you're going a little, you're actually moving a vector. When you're turning, you're reorienting. So you're laying down these little vectors. And if you look at the differential equation for a circle in Cartesian coordinates, it's pretty complicated. But think about the differential equation in inertial coordinates. Right? The change in curvature is 0. dc equals 0. And you've got the computer there to just integrate this thing. That's what the repeat is doing. It's actually adding those vectors to each other. And all of a sudden, you've got these kids into a place that's much stronger than most high school kids ever get to in high school calculus. And it's a thing where they can use their body intuitions about moving around the world. And they can learn numbers as vectors rather than just scalars. And et cetera, et cetera. So this completely blew my mind. I was just sitting there incredulous because somebody had finally shown me what a computer was really good for. And that is to help a child learn to think better than most adults think today. And if you think about all the problems in the world, virtually all of them are due to how badly most adults think. So it's not a question of pumping knowledge into kids, because there are plenty of knowledgeable people who think badly. So it's outlook and perspective and meta-thinking. So this just shook me. And on the plane back from that visit, I drew this little cartoon showing two kids with a kiddie computer, because of course you don't want to give kids a desktop computer, they're mobile. So I started thinking about Moore's Law for the first time and realized, oh, Moore's Law isn't just about making mainframes have more margins. Moore's Law means we can have personal computers, serious ones where the person part of personal computing is more important. And it turned out that ARPA, as well as doing the ARPANET that became the Internet, was also working with wireless. So I decided, oh yeah, it has wireless. Sure, why not? Let's just do, let me just see if I can plug this in here. I'm not good at time sharing. Okay. Now, then this wonderful thing happened. The ARPA funding was going away, but Bob Taylor, who was one of the ARPA funders, decided to try and talk Xerox into funding a bunch of these former graduate students of his. He had paid for all of our PhDs. And in the 70s, a bunch of inventions here. So personal computer with bitmap screen, object-oriented programming, the GUI, various kinds of interactive digital media, the laser printer, the Ethernet, and part of the Internet were all done by about 25 people in less than 5 years. So in today's American dollars, which would, let's see, what is the conversion factor? So $10 million a year in American dollars is what PARC cost in today's American dollars. So is that like 13 million in Singapore? Huh? $15 million a year in Singapore. See, this is what's interesting. Singapore has got all kinds of money. 15 million bucks, and you can invent an entirely new computing technology and take over the world. So what was the wealth generated by this? It's just a hair short of 20 trillion American dollars. 30 trillion Singaporean dollars. That sounds like a lot. And the thing to notice here is that hardly any of the solutions here were the ones that were thought about in the 60s. Not a mainframe in sight. Do everything with no switch networks. Don't worry about what the control keys are going to be. And so if we look at kind of the themes here, where think ahead to a real future is going to be laptops. Forget about anything in between. Think your way out there. Include children as users because time passes. And so the adults are terrible at learning. So if you aim computers at adults, you're going to delay things by 50 years or so. That's basically what's going on right now, by the way, since 1980. They're aimed at adults. Bad idea. So new ways to program, new user interface designs. You're familiar with this. So an interesting thing about what was done at PARC here was that there was no operating system. If you've got objects, you don't need an operating system. So that simplified things right away. We didn't have to worry about that. Just get rid of the operating system. And if you've got objects, you don't need applications, because who wants to stovepipe a few selected objects and not be able to mix and match them? Right? So think about what you really want is every object that is useful in one little bin where you can just plop it out and combine it in some media way. So that's what we did at PARC. You might wonder, why is the window interface today the way it is? Well, it's because other people wanted to retain files. Other people wanted to retain applications. People wanted to sell applications. People wanted to compete. So you actually get kind of a mismatch. Okay? So once you know what you want to do, then you can invent some hardware. Because I can't imagine what hardware is good for if it isn't to make software run faster. All right, now think about today. Today we have separate companies inventing hardware and expect software people to make the hardware look good. That can't possibly be reasonable. Think about it. And in fact, the graphics accelerator people ignored this. Graphics accelerator people said, hey, we know what the software is going to do. It's already there. Silicon Graphics defined it for us. We'll make something that will run that stuff really fast. Whereas if you look at the Intel and Motorola CPUs, nothing could be stupider than to have them just churning out these things without thinking about. For example, most higher level software requires something called a virtual machine. How well do these processors from 35 years ago run virtual machines? Well, they don't run them well at all. And then you've got something where you can do a lot of invention. And you've got to hook it all together. And it happens that 4 of the people on this slide are actually still colleagues or working with Viewpoints Research. We haven't died off yet. I'm just trying to show you a kind of a progression here. Now, what kind of proposal do we have to write to Bob Taylor at Xerox PARC to do this? That's right. Nothing. Why? Well, because Taylor was a manager. He didn't want to read any proposal written by a technical person. The reason he hired us was precisely to decide what to do. Sound weird? So if you think about it, when funders give out money and attach goals to it, if those goals are too specific or they want some sort of specific deliverable, what are you going to get? You're going to get D, not R. Doesn't matter what they call it. NSF in the United States has this awful thing. They want you to tell them in your proposal just what it is you're going to get done after you spend their money. How is that possible? Only if you do something uninteresting or something that's basically engineering. What you really want is to pick something that has some vision. And the vision is going to require lots of experiments. So what you can do in a proposal, that's why all of the ARPA proposals were 1 page long. They're basically saying, boy, it would be great if be great if we could just sit on a display and draw on a bridge and have the computer automatically calculate the stresses and strains on the bridge, or put in a building, or put in an electric circuit, or that'd be really great if we could do that. So that's all Ivan Sutherland ever had to say to get his funding to invent computer graphics. He had no idea what he was going to wind up with. It turned out he wound up with one of the greatest things ever done by a computer scientist. He didn't know that, and the funders didn't know that. Same thing with the Xerox thing. Could have been a bust. Actually, this guy right here, Butler Lamson, this guy, these three guys here, Taylor, Chuck Thacker, who did the hardware, Butler Lamson, who is one of the most amazing computer scientists who's ever lived, and then a few of the rest of us, we were extremely lucky in the particular way we went about this. We all realized that. We just happened to pick a good pathway, and we had the right people to meet up with that pathway. Could have been a complete smash, but of course if it was, then I wouldn't be here. So the success stories are the ones that tend to be talked about. Now the last few years, what we've been doing is basically trying to deal with massively parallel distributed computing. So for people who are interested in that stuff, opencroquet.org is a website. This is basically Dave Reed's thesis from 1978 at MIT, in which he proposed a way of distributing objects around large, slow networks and being able to absolutely coordinate them without using semaphores or monitors by using a pseudo-time idea like Simula used, and performing atomic transactions on the state in pseudo-time. So this is a great thesis, but it never got implemented, and a few years ago we decided to implement it. And this was one in which we didn't write any proposal at all because it would have frightened everybody. So we just used our own internal funds and did it, but it actually works, and anybody who's interested in this. So this is what's nice about this is you don't require any servers at all to do something like Second Life. It only requires the computer each user has, and it's a completely peer-to-peer and massively parallel, right? Because servers don't scale, right? The power set. So the number of groups, if you have 100 users on a network, the number of possible groups is the power set. 2 to the 100th, there are only about 2 to the 70th electrons in the entire universe. So please do not try to do scalable computing using servers. The internet doesn't have servers as its basic architecture, and that's why. And out of that we did this stuff we call eToys, which is a way of learning powerful ideas for children. I'll show you a little bit about that, and lots of experiments with children. And then over the last couple of years we've been working with Nicholas Negroponte on the marvelous $100 laptop. And I will show the talk about the laptop in the talk I'm giving tomorrow somewhere. I don't know where my talk is, but I'm not going to say much more about it today, except it turned out pretty well. And this is an example of something, by the way, that 20 people did. And the decision to do it was 2 years ago. And Nicholas had to go out and raise the money. He had to find buyers in countries around the world. He had to convince a Chinese manufacturer to manufacture the thing. And this is one of the first 1,000 from the factory in Shanghai from last November. So in less than 2 years, the complete machine and a new display had to be developed for this. So I'll talk about that tomorrow. So this is the kind of thing that any serious university should be able to do. Come on, guys. What do you think this is all about? So you sit down and write the operating system for it. Or even better, figure out that you don't need an operating system and do the next level of architecture. But So I used to be a professional musician, and in most universities, most high schools, there are classes called music appreciation classes. This is where people go in and don't play music. They listen to music on a hi-fi, and some teacher explains to them, yes, and this is the second theme from the Sonata Allegro movement. No. Imagine sitting in a room and having somebody explain tennis to you. It doesn't work that way. So basically, and I won't say anything about NUS because I don't know about it, but I can say in America that most kids who are taking computer science in college aren't doing it. They aren't doing anything interesting. They're learning mainly bad old ideas from the past, including some of the ones we invented. Remember, bits have no half-life. You can't get rid of bits, but ideas almost always do. So if only the bits would decay the way the ideas do. Okay, now here's one of my favorite books. Anybody who's interested in media, particularly interactive digital media, should read this book, Amusing Ourselves to Death. Fantastic book. Basically about television. But it was written before personal computing really got going and the internet really got going. And to broaden this out a little bit, this book is really about distracting ourselves to death. Remember I talked about Linux being a distractor? So all the crap that's on the internet is potentially useful, but it's basically a distractor. Most of these things are distractors. And so the problem here is you can make a lot of money making distractions. And it's true that people need a little bit of distraction. They need a little bit of amusement. You can't be grimly on task 24 hours a day. But the problem is the balance has shifted, and it's infinitely easier to make distractions than to make good ideas. Right? Most ideas are medium down to bad. It's just the nature. It's hard to have a good idea. But any idea can be a distractor if it's easy to replicate. So the internet is full of medium down to bad ideas that people spend endless hours dealing with. And it's interesting, in Singapore, there is, I believe, a correct policy about drugs. I don't believe in capital punishment, but I believe that a good theory about addictive drugs is no. It's a simple idea. But I don't think the Singaporean government quite realizes that television is a drug, that any number of things on the internet are a drug and have addictive behavior. People are studying this. And they also have the real difficulty of making us think that an enormous world of something, like in America it would be television, 24/7, hundreds of channels, seems like it's everything that could be. Whereas in fact it's only a few % of what's interesting in humanity, because it aims at one part of what humans are about. And so it has this dangerous thing of making people who watch television redefine their idea of normalcy. Right? So anything that's in an environmental form starts to become normal. You learn to navigate through it. It doesn't control your thinking, but it makes it difficult to think about other things. And you can use that in a positive way. So school, education is supposed to redefine our notion of normalcy. Right? If we were just using human common sense, we'd still be in caves. So learning and education and invention change the idea of normalcy. And you can change normalcy into something trivial, more trivial than what we've got, or you can change it into something that's less trivial. So here are a few grand challenges. I'm using pretty much the same themes because I want to emphasize that these are by no means global absolute ones. These are my personal favorites, the ones that I think are important. So I think we need to understand more about ideas, and especially for children. We need to understand how to represent them, especially for children and for explaining. I think storytelling is important, but in fact, perhaps too much of it is going on already. The most striking thing about the invention of science is that it did not involve stories. So in order to understand science and modern discourse about political systems, you have to wean yourself away from good stories, thinking stories that seem apt and pleasant might be true, whereas the opposite is almost always the case. Good stories are rarely true. That's not what we use stories for. So I'm interested in those two. New user interfaces, I might get to say something, maybe not. So the two things I think are most important in user interfaces that we don't see still very well today. One is, how can users express their intentions? So one of the things that has had little blips, maybe making a little bit of a comeback, is the idea that it's not just about dragging something with a mouse. It's not just about typing a number into a parameter, but it has something to do with being able to not just read the computer, which means being able to understand the user interface, but also being able to write the computer, which means to be able to do something like scripting, but scripting to some end user purpose. So HyperCard perhaps was the classic good example from 20 years ago. It just was really, for its time, it was brilliant, absolutely brilliant. And it's kind of faded as far as the general public, partly because the browser people in their ignorance did not use the HyperCard model when they did the first browsers, and no browser today has that model of not just consuming the media, but also being able to construct that medium. Slowly maybe being reinvented. We call some of this reinvention reinventing the flat tire, because if you think of what a wiki editing is, wiki editing, you have to go into a special mode for most wikis to edit it, and that's in spite of the fact that WYSIWYG editing was invented in the 70s. HyperCard was invented in the 80s. And so when we get to the browser in the 90s, suddenly all of that is taken away from us, even though it was possible to do it on an Apple II. That is really dumb, and it's very hurtful. And then at the technical end here, I think that programming has actually slid a bit. It's hard to find a programming language that people program in today that is quite up to the Xerox PARC Smalltalk. In fact, I'm actually using the Xerox PARC system here to give this presentation. That's why I don't have to go into a mode to move something around. Because why have a mode? All right, and even if I want to take something that's actually a button here, so here's a button that's going to go to my next slide, I don't have to go into a mode to deal with that guy either. So let me just look at a couple of things here just to have you think. And this is a talk that was designed to end more or less an hour after I started. So I'll just get you to think about this comparison. So at home I have an Encyclopedia Britannica, 14th edition. So it has 1,000 pages in each volume. That's about 1.5 inches thick. So if you stack up volumes of these things, it takes about 11,000 to have page thickness up to the top of the Empire State Building. And there's 1,000 pages in each one of those, so you have this many. So you have like 11 million pages. And so that's about 560 million lines of text. Now it's disgusting that this number actually starts meeting some of the sizes of programming systems that we know today. For instance, Windows is at least, XP is at least 100 million lines of code. Of course, Vista is much larger. And the Windows apps, just in Microsoft ones, are another 120 million lines of code. And if you have some Adobe stuff in there and so forth. Now the problem is our brains haven't changed. So nobody can actually understand. There's only one way you can deal with something like this, and that is to add on to it from the outside. Right, just the way the Egyptians made pyramids. But this really, as a mathematician, this disgusts me because Maxwell's equations were originally much larger than this. But Helmholtz, Heaviside, and a few other people decided to try and find a way of portraying them mathematically so you could sort of see what they are. So they came up with these operators of gradient and curl in order to express these things. And as soon as they expressed them in a form that you could actually look at them with your eyes, people noticed that there was an asymmetry between the electric field and the magnetic field. And I should have a little arrow. That asymmetry led several people, including Einstein, to decide, well, there shouldn't be an asymmetry. And that led to the special theory of relativity. And here's my passport. Doesn't have anything interesting in it at all, just all the places I've been. But here's a book just exactly the same size as the passport. It's the American Constitution. It's the kernel of an operating system that has been running for hundreds of years with not terribly cooperating parts. Think about that. The case law in the United States is about 3 cubic miles of paper. It's far larger than stacking up the Empire State Building. These are all the specific things that thousands and thousands of lawyers contending with each other have written special cases of. It is not remotely consistent. It's open to interpretation. It reasons from precedent rather than using logic. It's a mess. And in fact, it looks just like most of our software today. So, if you like to design systems, then you got to just not like this guy. But we don't know how to do this guy. So the Empire State Building here was actually built by less than 3,000 people in less than 11 months, including the demolition of the old site. Now think about that. It was occupied in less than a year. How did they do it? 3,000 people. This thing was framed at the rate of 3 stories a day. They had a narrow gauge railroad on every floor. They had 3 times as many elevators running up the outside of the building than they have in the building today. The steel was still 110 degrees Fahrenheit because it was only 5 days from Pittsburgh to being put in the actual structure of this building. Now, if this is engineering, we don't have software engineering. We have no way, no knowledge of how to organize 3,000 people to do some major thing in less than a year. Period. So we've got stuff in the middle, though. We don't have to do things like the pyramid, which is before architecture. So no architect, no arch in the pyramid. In between are Gothic cathedrals, which give you things the size of the pyramid with 1/1,000,000th the material. So in the 70s, we thought that was objects, and actually it was. Not C++ objects, not Java objects, but real objects. Not objects masquerading as data structures, real objects. And there are a few other things. So if we look at progressions of various things, like from very, very tiny things up to more organized things, we get something that's turned out to be architecture, even though people have doubted this along the way. And my favorite slide here is these two guys with some math down here and some math at the top, and then the miracle in the middle. And when I was born, biology was still a miracle. 400 years ago, physics was a miracle. And I was 13 when Watson and Crick wrote their paper, and we're now up to multi-celled things like body plans. The biggest deal in the last 10 years is discovering how embryos organize themselves. And we're learning a little bit about animal behavior and so forth. And same deal when you're trying to do a system from the power supply on up to the end user. You've got all of this stuff to do in there. And we think it can be done much, much smaller and prettier by using about a dozen principles. And I'm not going to go through these principles. Most of these principles were invented by other people. But an interesting thing happened this summer is that we got $5 million from NSF out of the blue to actually do this very difficult project. And the project proposes to do this entire system from the end user down to the metal of the machine in just 20,000 lines of code. Not 200,000. Squeak is 200,000. Not 2 million, not 20 million, not 200 million. So basically you do the whole thing like this. And if I had a longer talk, I would show you some examples of how we might go about doing it, but I think if I'm reading the clock correctly up there, I should probably quit. So I think I will quit and leave possibly a couple of minutes for questions that anybody might have. So you can see this talk is a pep talk, right? If anybody's going to do anything in computing, it's going to be you guys who do it. Maybe you've got a couple of good professors who don't think they're so old. But the truth is the funders aren't going to do it. Most of the professors aren't going to do it. It's only... I was the oldest person at Xerox PARC, and I was 30. I was 1 year out of my PhD. And I didn't know how to write a proposal. I didn't know how to make a budget. And Bob Taylor gave me, 1 year out of my PhD, a sum of money equal to what I had to write many proposals to get this last year after doing all of these things. So I will never be more grateful in my life for people who can give researchers that opportunity. And believe me, when researchers of a high quality are given that opportunity, they almost always come through with something really big. That's you. It's just amazing how much can be done once you forget about... In fact, I've got a great slide, my actual ending slide. One of my favorite quotes. It's an American author, Susan Sontag, said, "All understanding begins with our not accepting the world as it appears." Now, you've been taught all of your life to accept the world as it appears, and to accept your culture as it appears, and accept. But if you can just break free of it, then all of a sudden you realize, oh, wait a minute, I had my eyes closed. If we didn't have a reflex to open them up, then we could go through our entire life not realizing we were blind. Okay, thank you.
I think we just have time for one question, unfortunately, because of a tight schedule. So, does anyone want to ask one question?
This is a test. Yay!
I'm down to one question. Okay, so that Cheok, has anyone else got a killer question? Okay.